We have now obtained the time of flight of a projectile launched on an incline. So now that puts us in a position from which computing the range of the projectile should be easy. Since we measure the range along the x-axis or along the incline, we will apply the second equation of motion along the x-axis in order to obtain the range. So here we have the second equation of motion. X minus x0 equals v0t plus half at squared. Now for the range, think in terms of only the x direction or along the incline. Now the initial displacement x0 is 0, that is the launch point of the projectile. The final displacement along the x-axis is the range r, which we want to compute. The initial velocity along the x-axis is v0 cos of alpha. The acceleration component along the x-axis is g sine beta, and its direction is opposite to that of the initial velocity, so this is in the negative x direction. So let's substitute for t the time of flight, which we had computed, as 2v0 sine of alpha over g cos beta. That's it for the physics. What follows now is pure mathematics. We substitute for t here and for t squared here. And we multiply and divide this first term by cos of beta. And now we observe a pattern, cos A cos B minus sin A sin B, which simplifies to cos of A plus B. So this will be cos of alpha plus beta in this case. So we get the range as 2v0 squared sine of alpha cos of alpha plus beta over g cos squared beta. This is the formula for the range of a projectile which is launched on an incline, and this formula for the range may seem a bit difficult to remember, but you only have to understand the concept, which is to rotate the axes and then apply the equations of motion. Later in the series, we will make a video which will help you remember these equations. Let's discuss one more way of obtaining the range, but with far fewer calculations. Now we switch back to the coordinate system, which is horizontal and vertical. Whatever the coordinate system, the time of flight from launch to landing will not change. This is the range of the projectile r, which is along the incline, which we want to compute. Let's say that the horizontal displacement of the projectile is RH. So RH can be considered as the range along the horizontal axis. Now along this horizontal direction, the advantage is that there is no acceleration, but in the x direction, which is along the incline, there is an acceleration of minus g sine beta. So in the horizontal direction, the velocity does not change, it remains constant. And that component of velocity in the horizontal direction is v0 times cos of alpha plus beta, which is along the ground or horizontal. Therefore, RH will be equal to this constant horizontal velocity times the time of flight. Now RH is r cos beta, and the time of flight we had already computed as 2v0 sine of alpha over g cos beta. And using this we arrive at exactly the same value of range. So if you understand these couple of steps, there is no need to memorize the range formula. All you need to memorize is the time of flight, which we will discuss in a later video on how you can easily memorize this. Let's move on now to solving a numerical problem on computing the range. We take the same problem as in the previous lesson. A projectile is fired at a speed of 70 meters per second on an incline of angle 20 degrees, at an angle of 45 degrees with respect to the ground. And we need to find the range along the incline. So the angle of launch alpha with respect to the incline will be 45 minus 20 or 25 degrees. Substituting V0 as 70, alpha as 25, g as 10 and beta as 20 and alpha plus beta as 45 into this range equation, we obtain the range as 331.67 meters, which is the value of r in this figure, which is along the incline. So now we have computed both the time of flight and the range, and you can see that apart from rotating the axes and resolving the velocity and acceleration vectors along these axes, we haven't added any new concept. We have simply used the equations of motion along each axis. To compute the range, we apply the second equation of motion along the x-axis, which is along the plane of the incline. We have to be careful in the equation that we substitute the components of velocity and acceleration which are along the x-axis, so parallel to the plane of the incline.